Hey guys, welcome back to another day of physics problem solving with Captain Hook. Today we're going to sort of put together what we've done in the last few times with some kinematics and some Newton's laws, putting all together. Again, just like always, you can see this problem below the video, but we'll go ahead and get started. So we have an problem says an exceptional standing jump would raise a person 0.80 meters off the ground. To do this, a 61 kilogram person crouches 0.20 meters and pushes off from the ground, exerting a force on it. By Newton's third law, the ground pushes back with an equal and opposite force, which accelerates the person off the ground. So part one says, what is the jumper's speed just as he leaves the ground? So first thing we're going to want to do is draw a picture so we know what's going on. We have our ground, obviously, right here. We have some person standing on it who is going to jump off. And when he jumps off, we know that he's going to jump to a height of 0.80 meters. Okay. We know that the person's mass is being pulled by gravity, F equals ma, which his mass, given his mass, is 61 kilograms. Okay. We also know that once he jumps, as soon as he's off the ground, the only force acting on him is that force of gravity. So we know that his acceleration while he's in the air is going to be that acceleration due to gravity of 9.8 meters per second squared. And we know that he's going to come up. He's going to get to this point. At some point, he's going to start falling back down. But as soon as he gets to this very top point, we can tell you that his final velocity at this top point right here, his final velocity has to be 0 because he goes from a positive velocity to a negative velocity when he starts falling back down. So we know that we can consider that a velocity at the very tip-top point has to be 0. Okay? So if we write down everything we know, again, we know that his mass is 61 kilograms. We know that his acceleration is 9.8 meters per second squared. We know that the change in his position is from 0 all the way up to 0.8. So I'll call that delta y because it's a change in the y direction of 0.8 meters. We know that his final velocity, once he gets to the very top, has to be 0 meters per second. And we're trying to figure out what his initial velocity was. So we don't know that, but I think we can figure it out. So if we go back and look at our kinematic equations from before, we could use almost any of them, but I am going to go and just choose this one. We have final velocity, initial velocity, acceleration, displacement, sort of all the stuff we need. So we're looking for this initial velocity. So what I'm going to start with is I'm going to start with just writing out the equation where we have final velocity equals initial velocity, each one squared, plus 2 times acceleration times the change in y position. If we do a little bit of algebra, we bring all that over, take the square root. We're going to get that the initial velocity is just the square root of the final velocity squared minus 2 times acceleration times change in y position. Okay? So we're going to plug it all in a little bit. We'll just plug in all the numbers, put it into a calculator. Well, final velocity, well, we know that that was 0, so we don't have to write that down here. We have negative 2 times negative 9.8 meters per second squared, because don't forget, gravity always acts down, times 0.8 meters. And if we plug all that into our calculator, we get a final velocity of 4.0 meters per second. So that's how fast he had to go as soon as he left the ground to get to 0.8 meters before gravity stopped him and started pulling him back down again. Okay? So that's our part one. Okay? If we go back here, we look at part two. It says, what force must he exert on the ground to perform this 0.80 meters jump? Okay? So we're going to go back, and we're going to draw another picture for just this beginning part. So again, we still have the ground here. We still have our guy standing on it. Okay? But now we have a couple forces. We have a force of him going up, which I'll just call F, and then we still have the force of gravity pulling him down, so we can't forget about that, because that's always there. Okay? But now, we want to know what force he has to do here, so that as soon as he takes off, which he bends down and he has a little displacement of 0.2 meters. So what kind of force does he need to do to get from 0 meters per second when he starts all the way to that 4.0 meters per second when he pushes off the ground? Okay? So again, we write down what we know, what we don't know. We know again that his mass is still 61 kilograms, that's not changed. We know that the acceleration, well, we don't know what that is yet. Let's figure out what his acceleration is. We know that his final velocity was at 4.0 meters per second because that's what he started at. Our initial velocity, in this case, because this is what he's using to push off, was 0 meters per second. And do we know what time is? Nope. But we know his change in position because it was at 0.2 meter push off. So our delta y, again, still up and down, is 0.2 meters. So we can actually go back and use that same equation we used in part 1, where we had vf squared equals vi squared, final velocity equals initial squared equals initial velocity squared, plus 2 times the acceleration times change in y. For this time, we want to solve for the acceleration, his net acceleration. It's causing him to move upwards. So we're going to subtract that over and then divide by 2 times change in position. So we're going to acceleration, get a little algebra, vf squared minus initial velocity squared over 2 times change in y. And we solve for that. So we're given a equals, well, final velocity was our 4.0 meters per second squared. Well, we know that initial started out not moving, so that was 0, over 2 times our acceleration, or times our change in position, which is 0.2 meters. So if we do all that, we get an acceleration of 40 meters per second squared. So that's how much he had to accelerate in order to get up to that 4 meters per second in that short distance. So we come back up here, and we can write our acceleration as 40 meters per second squared. Okay, but we weren't solving for acceleration. We want to know what kind of force he had to put in to make this work. So we got a little bit more work to do. Again, I'm just going to rewrite what we know. We know the mass was 61 kilograms. Our acceleration we now know was 40 meters per second squared. Our final velocity, again, hasn't changed, of 4.0 meters per second. Our initial velocity is now, or still 0 meters per second, because that's what he started. And our change in position is still 0.2 meters. But what are we looking for? We're actually looking for a force. So we're looking for a net force, or the force, well, a force for him to push off the ground. Now, when we deal with that, we're going to have to deal with a couple things. So if we draw him again, there's that. Again, there's our ground. We still know, we can't forget about gravity. So the force of him pushing up, which we called F, has to go against the force of gravity pushing down. So in this case, we're actually trying to solve for what his force is. Okay? So again, we have to figure out know that net force is the sum of these two. Remember, force of gravity is probably going to be negative because it's pointing down. So if we do net force equals the force of him pushing plus the force of gravity. Well, we know net force has to be his mass times his acceleration. So his acceleration times his mass, that's our net force. So we can actually go ahead and plug that in and say m times a. So his mass times his acceleration equals the force of up plus the force of gravity. Again, we're trying to solve for his force. So if we subtract the force of gravity to the other side, we're going to end up with his force equals ma, his mass times his acceleration, minus the force of gravity, which if I rewrite that, it's ma minus mg. So again, we can plug all that in. We get the force of him pushing up equals his mass, which is 61 kilograms, times his acceleration, which we just solved was 40 meters per second squared, minus force of gravity, which is 61 kilograms. minus, so don't forget gravity is down, 9.8 meters per second squared. Well, if we reorganize this, the masses can come out, so 61 kilograms times, well, 40 meters per second squared, plus, because our negatives cancel out, .8 meters per second squared. And that's going to give us a total force, if we do the math on all that, of 3,050 newtons. So that's how much force he had to push to cancel out gravity and to speed up in 0.2 meters to get to 4 meters per second.